Everyone, how are we doing? We got audio, we got video. It is warm in the office and the internet was down this morning. Oh my gosh. If you were on campus, you know what I'm talking about. We didn't have internet, but now we got the internet back and I'm wearing the green shirt again. That slightly goes away. I think we'll start up some My Pearson here. Can I hear my music again? Yes, I can. Reset the computer, updated the computer, and I thought that did it. I came into my office, the computer said it needed an update, and I was here, and I had like 20 minutes for office hours, and I was like, let me update the computer. And then I update the computer, and I log back on, the internet doesn't work. It literally happened like in that moment in the 5-minute update. I was like, are you kidding me? Well, because I originally thought it was the update. And I was like, okay, the update broke the internet. I was like, that's weird. Update just breaks the internet. You never know. We're gonna go do some My Pearson, I think. I'm gonna go look for the most recent homework. Get some homework and quizzes done. Might do the full homework because we only got a little bit of time this morning. An hour to do some work. Let's go look. It's some chapter 16 on type 1, type 2 error. Rolling all the way down right here. Chapter 16 is due tomorrow. So let's open up some chapter 16 homework and let's do the full homework. Those who are watching. Hey guys, I saw some students today. They were happy to see me. They were like, oh, I use your office hours. So you know what? It goes out to you. Office hours right here for you, for everybody. No one's in the chat yet, but maybe people will show up. Mubot's not even here. Let's get Mubot awake. He's just there crashing the internet. Mubot, you waking up? You waking up, Mubot? Okay, so we are here at the 2, 4 to 3 mark. Chapter 16 homework. Let's do this. Over to the main screen. Okay, chapter 16 homework. Chapter 16. Hey, Space Cat, good to see you. Let me know if you have questions. Chapter 16 is called More on Tests. So we go into more detail on the whole idea of p-values and alpha and type 1 error and type 2 error and beta. Those terms don't make sense. We're going to talk about them right here. So which of the following are true? So when it comes to p-values are probabilities. As in, you can tell someone the probability it's going to rain today is 1%. That would mean it's unlikely it's going to rain today. But when we do a p-value, it's the probability the null is true. The probability of what we saw given the null is true. My brain's still rebooting like the computer. The probability of what we saw in our data given the null is true. So a p-value of 0.01 means the null is false. Not quite. It would mean we have significant evidence to reject the null. It means what we saw in the data was not likely, because remember, it's a probability. P-values are probabilities of what we saw given the null is true. Yeah, this right here, it provides evidence. We never really show the null is false. We just either give evidence or fail to give evidence. When we give evidence against the null, it's because what we saw was unlikely in our data given the null is true. As in, I always use the example of like, if I tell you I can run a 5-minute mile and you see me running 10-minute miles, that'd be a low p-value because you watching me run the 10-minute miles is not likely given I am a 5-minute mile runner. But if you see me running 501, 502, the p-value would probably be pretty high because that's a likely result given the null of I can run a 5-minute mile. So that should be the answer for this first one. The second one says a p-value of 0.01 means that the null has a 0.01 chance of being true. Remember we said the p-value is the probability of our results. It's the probability of what you saw given the null is true. So it's a conditional probability. Another example would be, let's say you believe the average student spends $10 on food a week, or that'd be so small, spends $70 on food a week. And so then you go out and you see students spending $500. So this doesn't mean the null has a 1% chance of being true. It would mean if this had a p-value of 1, it'd be way less than 1%. It'd mean what you saw the $500 students spend has a 1% chance of occurring given the null is true. So what you saw was unlikely given the null is true, so we'd reject the null. This is false. The p-value is not the probability the null hypothesis is true. It's the probability of our results given the null is true. The p-value of 0.01 is evidence against the null. Oh, that's true. Yeah, p-value is low, reject the null, have evidence for the alternative. So it's evidence against the null, evidence for the alternative. A p-value of 0.01 means we should definitely reject the null. Pretty much. I'm not reading their answers. It depends on alpha. We reject the null when the p-value is less than alpha, and usually alpha, which is the point of significance, is assumed to be 0.05. So in most cases, yes. So definitely is where I take issue. They might, see right here, whether a p-value provides enough evidence to reject the null depends on the alpha level. And in most cases, you would reject because 0.01 is less than alpha. That is really a very good theory question, and kind of knowing the answers before reading them is the key to being like, well, when do we reject the null? When the p-value is less than alpha. 0.01 is usually when we'd reject the null. It's very common to have a 0.05 p-value, but you don't have to. You could use a 0.001 p-value. Alpha. Savannah, good to see you here. Sorry for the late start. You might know it, but the internet was down. So, man, these Mondays are just crazy. I'll put even question 1 in here on the homework so people can come back and view this. Question 1. And hopefully people watch that because that was just good theory, just talking through it. 633, chapter 16, homework, question 2. We're going to try to do the whole homework here, so check it out. More true false. These are really good practice. Using an alpha level of 0.05, a p-value of 0.02 results in rejecting the null. Let's draw something out right here real quick. Alpha, you should know what alpha is. Alpha is literally the point at which you reject the null. So that's what alpha is. Alpha, we're going to show the screen here in a second. Alpha is merely the point at which you reject the null. So just make sure you keep telling yourself that. Alpha is my point at which I reject the null. So what you want to imagine right here, really, gosh, computer, stop acting crazy. Sure, there we go. You want to imagine there's a bar. Sarah, good to see you there. And the bar is alpha. Now, unless otherwise stated, alpha is 0.05 by a problem. Now, your p-value, if your p-value ends up here, something like 0.06, or technically even right at 0.05, because it's at or above alpha, then you do not reject. So this is do not reject. But if you reject the null, this is the HO, the null, and if your p-value is below alpha, like a p-value of 0.02 or something, which this one says, you will reject the null and say you have evidence to the alternative. So what is alpha? Alpha is just a point at which you choose to reject the null. You can set alpha to whatever you want. It's generally 0.05. We don't play games with alpha a lot of times. Why is it 0.05? Probably because people have done it that way for a very long time. And it's a very unlikely thing to see something that would only happen 5% of the time. So, oh my gosh, got all the documents open while we email and everything. Open up. So yeah, this is just flat out true. You're using an alpha level 0.05, a p-value of 0.02 results in rejecting the null. It's true, and they give a good explanation right there. You see Catherine, ask any questions you got. We're doing the full homework, chapter 16 homework. The alpha level depends on the sample size. No, researcher just comes up with it. You just say, I want a 0.01 alpha level, 0.02, 0.05, 0.010, use 0.05 normally. Researcher just comes up with it. So it's dependent and cannot be determined. It's not always 0.05, that's a lie. Yeah, it's set independently. You just come up with it, whatever you want it to be. With an alpha level 0.01, so that's the rejection criteria. A p-value of 0.08 results in rejecting. No, your p-value is higher. When the p-value is high, just let the null fly. The same is false because only a p-value less than alpha results in rejecting the null. Very true. That's when we reject the null. You should know these things flat out. A p-value less than alpha results in rejecting the null. That is a very strong thing to know for the class. Using an alpha level of 0.05, a p-value of 0.06 means the null is true. No, doesn't mean the null is true. We just didn't have enough evidence to reject the null. We didn't have sufficient evidence. The null is probably false. I mean, if I had to bet, but we're not going to go with the alternative yet. We want stronger evidence. So, but if you made me make a bet on it, so you'd say, well, why don't you just say the null is false then? Well, until we get better evidence, then I'll reject the null and have a new alternative. But we like to go with strong evidence and statistics rather than weak evidence. So we would continue on. The null is usually something we've believed historically, and so we're not going to change our views on a whim. We need strong evidence. But yeah, so this right here is false. We don't say the null is true. The same is false. P-value greater than alpha only indicates there's not enough evidence to reject the null. We do not say the null is true. Once again, really kind of tricky questions, but very good theory questions. And a lot of the answers pop out to me, probably because I've been teaching this for 14 years, but knowing the theory is the key. So these are all theory things. There's like a mini lecture right here on understanding these topics. We'll do another one right here. It is better to use an alpha level 0.05 than an alpha level 0.01. It's just researcher preference. I mean, there's a trade-off. Alpha level is your type 1 error rate. So you'd have a higher type 1 error. But if you have a higher type 1 error, you have a lower type 2. They are inversely related. Type 1 goes up, alpha goes up, type 2 goes down, beta goes down. So it's false. False, a lower alpha level lowers the probability of type 1 error. True. But increases type 2. It's exactly what I said. It's a trade-off. there's no perfect. There's no way to not make errors. This one says, if we use an alpha level of 0.01, then the p-value of 0.001, yeah, that is just a fact. When is something statistically significant? Go back to your sheet right here. Statistically significant just means what? Does anyone know in the chat we haven't thrown any points today? What does statistically significant mean? If I say statistically significant, what does it mean? This is what it means. Statistically significant just means what? If you're in the chat, say it. Oh, let's see what they say. Statistically significant just means p-value less than alpha. P-value less than alpha. So if you want to know if this is statistically significant, you say, this p-value, is it less than alpha? Yes, it is statistically significant. So that's a fact. There we go. If we use an alpha level 0.01, then we can reject the null hypothesis if the p-value is kind of repetitive. That's the same thing. That's when you reject the null. That's what statistically significant means. So yeah, you're trying to trick me? That's the same thing. That is literally just rewording. Rejecting the null means you have statistically significant evidence. It means the p-value is below 0.05. It should be like, great job. Both those questions tested you on the same knowledge. I thought it was a trick. Good to see you there. More in the chat. We're doing some stats today. Let me know if you got stats questions. So this one says if the p-value is 0.01, rejecting the null, we reject the null for any alpha level greater than 0.01. That's also true. This is an interesting one. So what they're saying is, and check it out visually here, they're saying if the p-value is equal to, Mubot's talking there in the chat, so they say if you have a p-value of equal to 0.01, you wouldn't set your alpha level afterwards, and then you have an alpha level that is greater than 0.01, then you would reject the null. And that's a fact because this bar, so the way I'm drawing this is if the p-value were to be something higher, like p-value of equal to 0.08, that would be above an alpha of 0.01. Now they're not saying use a 0.01 alpha, they're saying any alpha level above 0.01, like 0.02, 0.03, 0.022. But this would be true because then the alpha would be greater than the p-value. A little tricky with all those truths right there. Now we get to one of my favorite things right here. What is a type 1, type 2 error? Well, we haven't talked, that's not it right yet. I'll be coming shortly. All these terms. Now, if you're watching this, this is going to be a quick click to the right answer. Let's mark this in the video though. Because what I want you to realize, hopefully you're listening to me, is you should know every one of these terms. I'll go into more detail on them as we talk through this, but every single one of these on the screen, you should know. It says, what is the name of the threshold p-value that determines when we reject the null? We've already been talking about that a lot today. Critical value is the t or the z. It's the test statistic by which we reject the null. We don't usually use critical values. They can also be used for intervals to say the critical value that makes the interval. It's a t or a z. So that is a test statistic, what is a critical value. Type 1 error is when the null is true and we reject it. Type 1, the null is true and we reject it. Alpha level is the level of significance which determines at the point we reject the null. So the alpha level right here, as you can see, the alpha is the point at which we reject the null. So that's what alpha level is, and that's the answer to the question. Effect size is the difference between the null and the truth. So if the null is, let's say that students are only 5 feet tall. There are some students who are 5 feet tall, but we're saying on average. And then you go out and collect data and you find out the average student is 5'10", that's a bigger effect than having the null that the students are 5'9". Or if someone were to tell you, I think students only spend like $10 a week on groceries, you're like, really? Like, yeah, students don't buy groceries. And you're like, and you collect data and you find out they spend $100 a week on groceries. Well, that's a $90 effect. And we don't know what the truth is. We only have an estimate of the truth, but you estimate the effect to be $90. Now, if someone else came along and said, I think someone spends $99 a week on groceries, the average student, and then you find out $100, that's an effect of only 1, and it'd be very hard to reject the null. Effect size is the true difference, which we only estimate a lot of times between the null and the truth, what the actual distance is. When there's a bigger effect, it's easier to observe because then you can see it. You can say like, wow, you think students only spend $10? We estimate the effect to be 90, the difference between your null of $10 and our estimated truth of 100. So effect size is not the answer, but it's a good thing to know. Know those terms. Effect size is one of the 3 things that impact statistical power with alpha, effect size, and sample size. Alpha, effect size, and sample size are the 3 things that impact statistical power. Question 5 right here. Okay, if the p-value is smaller than the level of significance, what should we do? These are very, very repetitive, and I hope everyone knows them by now. You should see this and be like, well, yeah, if the p-value is low, reject the null. I want to write this out for you once again and have this and know this. When the p-value is low, reject the null. What do we mean here? When the p-value is lower than the value of alpha, which is assumed to be 0.05 unless otherwise stated, reject the null. When the p-value is high, just let it fly. I'll put this one next to it right here. This is the short version, the memorized version. That's the long, trying to understand what you're talking about. When the p-value is higher than the value of alpha set by the researcher, then just let the null be, or we should write it in actual wording, then fail to reject the null, and you do not have evidence for the alternative. Reject the null, you have evidence for your alternative. Sufficient evidence, evidence for your alternative. So these are the sayings I like to say to memorize this. When the p-value is low, reject the null. When the p-value is high, just let it fly. So here's the more in-depth to make sure you understand it. When the p-value is lower than alpha, which is what we assume to be 0.05 unless otherwise stated, that's just that bar we came up with. If we go under the bar with our p-value, we reject the null. Then we reject the null, we say it's statistically significant, and we have evidence for the alternative. Now, if the p-value is high up here, we do not reject the null, fail to reject. When the p-value is high, just let the null fly. So we do not reject the null, fail to reject the null, and you do not have evidence for your alternative. So I like the wording of I do not reject the null, I do not have evidence for the alternative, because it goes with like I do reject the null, I do have evidence. When p-value is low, I do not reject the null, I do not have evidence, because fail to reject just means did not reject. If I say I went to the mall, morning Joe, good to see you there. If I say I failed to go to the mall, I didn't go to the mall. We're finishing up the homework, we're pretty far in. So the p-value is low, reject the null. That's what it says. P-value low, reject the null. We're almost done with this. Pretty easy homework. Well, it's a lot of multiple choice. I think like conceptually it might be tricky and we're going into detail, but if you have a question, let me know. Was your internet down this morning, Joe? We'll throw you some points right here. We had the internet down, and so I just walked around, hung out, and then came up here. The internet was working again. So what is the probability that a test correctly rejects a false null? I know the answer to this immediately. I know, right? Here's what you need to memorize. 1, 2, true, false. In a type 1 error, the null is true and we reject it. That's a T. In a type 2 error, the null is false and we fail to reject it. That is, when people miss these on the test, because we almost put them verbatim on the test, I feel so bad because the two F's go with the type 2. Let me repeat those saying again. In a type 1 error, the null is true and we reject it. In a type 2 error, the null is false and we fail to reject it. So that is a type 2 error, and we can go into some examples of it. Memorize it. So what is the probability that, so actually I was mistaken. Those are type 1 to type 2 error, but it asks for a probability, not the scenario. Now, we have two other things on here. We have p-value, significance, and power of test. Two other wrong things. P-value is the probability of our results, or results more extreme, given the null is true. So p-values are probabilities, but this is not a p-value. Significance level is the point at which we reject, often noted as alpha, and alpha is usually assumed to be 0.05. Type 2 errors when the null is false and we fail to reject it. Now, the last one, the power of a test, is actually beta. Beta is the statistical, or 1 minus beta. Gosh, I need to wake up this morning. Beta is the probability of a type 2 error. Yep, which ones do you want to do on the quiz, Savannah? Let me know. We got a little bit extra time. So beta is the probability of a type 2 error. 1 minus beta is the power of a test. And the power of a test is the probability of not making a type 2 error, which is the probability we correctly reject the false null. So, and it literally says it right here, 1 minus beta is power. where beta is type 2 error. And once again, write these notes down. Beta is type 2 error. Power is 1 minus beta, so it's the complement of beta. It's not making a type 2 error, so it's rejecting the null when the null is false, because the type 2 error is when we fail to reject the null and the null is false. So type 2, or power, is correctly rejecting the false null, and that's often how it's phrased. What is the name? Commonly, you got it. We'll do that one here next after the homework. We'll finish the homework. We're almost done with it. A little bit faster. Get the homework done. Thank you, Savannah. I'm gonna be done with the homework and the quiz. Have you already done the homework? It's a lot of multiple choice, so like if you don't get hundreds on this, I'll feel like, no, you can just redo. What is the name of the difference between the value in the null and the true parameter? So if you've been watching earlier, I mentioned it. Do you know which one this is? ABC, Savannah, for some points. What's the difference between the null and the truth? The difference between the null and the true value is what? What is that called? Alpha is the point at which we reject. So it'll be effect size. Effect size is the difference between the null and the truth. And so that's the effect something has. Good answers. Points in the chat. Good practice. Alpha is and we'll just look at the other answers. Alpha is the point at which we reject. Critical values are used for tests or intervals to make them. They're the Z or the T. Type 1 errors when the null is true and we reject it. And effect size is the true difference between the null and the truth. No worries. We're throwing out points left and right. So really good type 1, type 2 error question coming up right here. Sid, you got it. We'll do those two next. Thank you, Savannah. Like, you'll come back and watch these videos, I know, and then they can help with the questions. Question 8. 2 more questions, then Savannah's questions coming right up. For each of the situations in part A through D, state whether it's a type 1 or type 2 error. Repeat after me. In a type 1 error, the null is true and we reject it. In a type 2 error, the null is false and we fail to reject it. Or if no error has been made, that they made the correct decision. There's a weird one in here. Hopefully I don't miss it. It's a weird one. We'll find out. A bank wants to know, 8 points. A bank wants to know if the enrollment on their website is above 30% based on small samples of customers. They test the null that the proportion is 30% versus the alternative that the proportion is greater than 30%. Notice how I read that, read it as a sentence, and reject the null. So they could have only made a type 1 error here because they rejected the null. In a type 1 error, the null is true and they reject it. But they might have done the right thing. Sometimes you don't make errors. Later they find out it's actually 28%. So they shouldn't have rejected the null. It's actually lower. This is gonna be interesting. This might be the trick one. See, it's between these two because the way they're wording it, they did make a type 1 error because they shouldn't have rejected the null. The actual value is not greater than 0.3, but they rejected the null. In fact, the actual value is close to 0.3, but it is. It's kind of close. It's factual that it's not greater than. So I'm just going to click that. There we go. Really, once again, I don't like that because that's tricky. If you wrote that on the test, I'd give you credit. It's like it's close to it, but it's not greater than, because that's what they said they have evidence for. They said we have evidence that's greater than 0.3, and no, they don't. They don't have evidence that's greater than. Well, they do. They did have evidence, but in great job, Samantha, right there, they were wrong. So they had evidence and they rejected the null when they shouldn't have. It's just how errors are made. A student tests 100 students to determine whether or not students prefer soda, brand A or brand B, finds no evidence of a difference. So they failed to reject the null. Later, a marketing company tests and finds no difference. So they fail to reject the null. So we would assume at this point that no error has been made. We don't, I guess they test all students. They did a census. So that's the only way they'd know the truth. So in their theoretical example, they know the truth. Great job, Savannah. A human resource analyst wants to know if the applicants this year on average have a higher placement exam. So looking for mu greater than 52.5. She samples 50 and finds the average to be higher. She fails to reject the null, so she could have made a type 2. At the end of the year, the candidates did have a higher. So she failed to reject the false null. The null was false. Great. Wow. Yeah. She failed to reject the false null. And a pharmaceutical company tests whether a drug lifts the headaches relief from 25% from placebo. So the true proportion of people who receive their headache relief is greater than 25%. They failed to reject the null, so they could have made a type 2 error. P-value is very high. Further tests analyze the drug actually relieves. So this is another type 2. The null hypothesis was not rejected, but it was false. Wow. I mean, A lot of people have trouble with these. I mean, we could do it another, we could go back over them, but wow. And what is the type of error when the null is true and it's rejected? Type 1 or 2 in the chat. Oh, please be careful. You got to know this one like that. When the null is true and it's rejected, what error is that? You got a 50-50 shot by chance. If you know the saying, you get it right every time. Which one is it? 1 or 2? 1. Ooh. Type 1 error is when the null is true and we reject. No worries, no worries. In a type 1 error, the null is true and rejected. Autumn, good to see you here. We've done the whole stats project last week. Check out that office hours. We have the whole, it's all labeled full stat project. We're about to do some chapter 16 quiz coming right up. So that is the full homework right there, full homework in the video. We got 2 questions, I think, on the way. Let's get the quiz up and going. We did the full project, start to finish. We can do Canvas. We do Canvas content real quick. I'm gonna do Canvas content really quick. Might have to do some office hours tomorrow too. Let's do Canvas content really quick. We haven't done Canvas content. No, well, we'll do it next. We'll do it in between. Because thank you, Savannah. Savannah's been here the whole time. And so I'm going to honor that and do Savannah's first question right here. Savannah says a company surveyed 2,500 men. We'll do that and then we'll do Canvas content. Thank you, Savannah. Shout out Savannah right there. And then we'll do some Canvas content. Thank you, everyone who's here. Good to see you. We got a crowd today. I like it. There's a lot of questions you get on this quiz. I need my second cup of coffee. Went to Starbucks and they said, nope. Imagine if they took money. Not the worker's fault. It's Starbucks' fault. I didn't have money on me though, so it's moot. Like, imagine if they took money, but I don't carry money. My wife does. And she tells me I should carry money, and she's right. And I say, but Starbucks won't carry money. Okay, let's go check out this first question right here. Here we go. And huge shout outs to the students I saw in Starbucks right there. Thank you so much. They were dealing with the storm. The people were walking up and being like, wait, I can't get my coffee. And it's like, sorry, yeah, I'm doing all right though. But I've worked in the service industry and man, people can be mean. So I appreciate it. It's just weird to me that Starbucks doesn't take money. And that's totally not the workers. That's Starbucks. That's their thing. So here's my money. And they say, what is this? Maybe they do take money. Maybe I'm wrong. I don't know. The heat's getting my house hot. Let's check out the conditions. Here we go. Condition 1, they need to randomly sample these men. And I assume it was a random sample. Condition 2, less than 10%. They need to sample less than 10% of all men. And last but not least, condition 3 says we need at least 10 successes, at least 10 failures. So yes, this is less than 10% of the population. I assume it is a random sample. We have the randomization is met. Oh my gosh. Randomization condition is met. And we will, what do we do next? Is it nearly normal or success failure? I already said it. Do we do nearly normal or success failure next? What do we do? The answer is success failure because it's categorical. Exactly. And there are 1,173 successes. And since we're doing a confidence interval, I believe that we would use the amount of successes. Now, the amount of failures, you can just subtract out of the total and get the amount of failures. And that's close enough. So it's technically NP hat and Q hat, but NP hat would be 1173 divided by 2300, and it's 51%. So NQ hat is 49% because they're complements. Make a 98% confidence interval. Now, to make a 98% confidence interval, we need to get the Z-score for a 98% confidence interval. What is the Z-score for a 98% confidence interval? What is the Z-score for a 98% confidence interval? Comes down to
notation, brother.
What is the Z-score for a 98% confidence interval? 2.3263. Oh my gosh. 2.3263. There we go. That's Z right there. And so that should be the Z-score. This is going to be N This is going to be X. If you're wondering how we got that z-score, Ubot's going to tell us about the applet here in a second, but the applet is the place you need to go to, 2.3263, yep. And so we're pulling up the applet right here, and to do a confidence interval, you need to go to find correct right here, between, and then go to 98%, not that. And there it is right there, 2.3263. 2 decimals is usually enough, but that is going to be the confidence interval z-score right there for us to use. There we go. Okay. And so now make the 98% confidence interval. Well, p hat is equal to x over n, the amount of successes over the number of trials. So 1173 over equals, and we said it equals to 51%. And if p hat equals that, then q hat equals to 49%. And now we write out the formula of p hat plus or minus z star, which this is the z star picked by the confidence level, times the square root of p hat, q hat, or n. That's the formula, which will be given to you on the test. We start plugging in the numbers of 51% plus or minus the z-score of 2.3263. Square root of 0.51, which was p hat, the proportion, over or times its complement over the 2300. And now we go right here and we do 0.51 times 0.49 divided by 2300. Square root, that is the standard error, which is basically square root, we square rooted it. It's basically 0.01 times 23263. Plus or minus the 0.51, and I think that's rounded enough, so we can just do the math ourselves of 0.51 because we're multiplying by a decimal here. 0.023, that should be rounded, and probably it's going to round up here to 33, so with a little extra change on there. And then we go plus or minus on this. We're just adding and subtracting on the 51, so we're going to get 0.05333, interesting. And then the lower amount is going to be subtracting, which is going to be 0.48 and then 67, because we're basically minusing a third off of there. So 48.67% to 53.33. Let's go back to the problem over here. So it wants it as a decimal, 3 decimals, 48.67, so that'll round up, and 0.533. What does the confidence interval say about the grocery store's hypothesis? Based on this interval, I am 98% confident. All right. Because 98, oh, they're talking about the thing they believe. We didn't even see. They believe 56%. 46, excuse me. Because 46% is not in the interval, we would not believe it. Thank you, Savannah. Good job. Because it's not in the interval, you notice right here they believe 46%, then we would reject it. So we do have evidence. We have evidence that more than 46% is the true proportion of men who are the primary grocery shopper. Determine the level of significance by which the test is done. So this is the way this works right here. We are trying to do a greater than test, I believe. He's asking to see if in fact higher than 46%. So the way this is done is confidence intervals and two-tailed tests are directly analogous. So if you do a confidence interval at 98%, the two-tailed test p-value, which is analogous to it, is what? So Savannah, what is this an analogous, like you would get the same result if you did a test with what alpha level? So this is a two-tailed test. So what would be the alpha level for the two-tailed test? Because they are complements. That answers the question. So this is the confidence interval at 98%, and this is an alpha level set to what? You get not 0.05, good answers. This would be 0.02 because it'll be the complement. So if you look at these right here, they're complements. So that's why oftentimes you'll hear like a 95% confidence interval. So when you hear 95% confidence, 95% confident is going to be analogous to a 5% alpha. So that's why a lot of people use 95% confident and 5% alpha. No worries. This is why right here we have 2%. Now, here's the thing, though. We're not doing the two-tailed test. We're only doing the one-tailed test. So we're doing a greater than test. So what is the analogous alpha level? So this is a little bit tricky, but we're doing the one-tailed test. So what is the so use the pictures to kind of clue you in. So it's basically drawn out now for you to figure out the analogous alpha level for the one-tailed test. You'd come to the same conclusion. What would it be for points in the chat? The analogous alpha level would be what? Just take a guess if you don't know it. So remember how it was 2% just a second ago? And then look what I'm doing visually. So when it was a does not equals, it's 2%, it's just the complement. And now we're talking about a greater than test. So it's going to be half, because you're only shading the one side. You're only shading this over here because these are the same value of 1% each. And since you're only shading half of what the 2% was, then the analogous alpha level is 1%. So that's the result right there. And we go here. Since the level of significance is this, since it's a one-tailed test, we have the area right here. There's having the area on the alpha of the outside. That should do it. Yeah, I was a little worried. A little tricky parts of that, so I was a little worried we might miss something, but you never know. Let's do the Canvas content. Those are fun. I like Canvas content. Do you like Canvas content? We all like Canvas content. Woo! We should make all the quizzes Canvas content. Every one of them. No Pearson. Sorry, Pearson. In a sassy mood today. Okay, logging in here. DARS report. Oh, that's what it stands for, Degree Audit Reporting System, DARS. I didn't even know what DARS stood for. Been here 24 years and don't even know what DARS is. What's going on with me? No DARS. You'll turn it in the project. Okay, when is Canvas content due? For a while? Oh, it's due to today. Oh, man. Oh, man. Canvas content due today. Good thing to get done. Okay. Right here, 3813. Chapter, or Canvas content. Canvas content 9, hypothesis testing. Okay, let's do it. So with Canvas content hypothesis testing, good morning, Millie. Good to see you there. We've got some nulls and alternatives. You know what? We can probably write it out. I'll assume that. How many of these answers are plausible? So you should know, when you look at this and as nulls and alternatives, you should be able to narrow it down to how many answers quickly. There's something we always say. So how could you narrow this down really quickly? Just being like, you should be down to a few answers. Anyone know? When you write nulls and alternatives, the null has the equal sign. The null has the equal sign. So we're literally just down to these two answers. So the null states that the mean weight loss is 10 pounds versus some alternative. Great job, Sarah. Yep. And now we just have to look at what they're trying to show. Inventors claim people lose 10 pounds on average. So they're probably trying to tell you, oh, you're trying to test their claim. Okay, you think they're exaggerating. So which one do you think it would be? You think they're exaggerating. You want to show that their claims are exaggerated. So it should be which one of these? B or these two right here, between these two. You think they're exaggerating. So which one should you pick? You think they're exaggerating. You want to show evidence of exaggeration. So which one should you pick? Well, the alternative is what you want to show evidence of. So you want to show evidence that the true mean weight loss is less than 10 pounds to show they're exaggerating. So this would show that they're actually doing better. It would be D. Great job, Malik, right there. You want to show evidence of less than, yeah. Because the alternative is what you're trying to show evidence of. I want to show you evidence that true mean weight loss is less than 10 pounds to show you exaggeration. A new diet is being tested. The inventor claims you lose 10 pounds. That's the null. After 25 people are randomly sampled to try the diet. Researchers investigate the claim. The sample yields a sample average of 5.5. The standard deviation is 6.1. Calculate the test statistic and enter to 2 decimals. Give me a second. Give me a second. Man, of course it's going to be tricky. Okay. So, oh, it's tough. The test statistic is something like -3. Oh man. -3.7878. That's what I say. Okay, let's go find out. Would I have gotten it right or wrong to 2 decimals? It would round up to this. Let's go do it. What do we have to know for this question? What is the key to solving this question? What is the key to solving this question? Who knows the key to solving this question? What is the key to solving it? Probably closer to 3.7. The last part. Used to be better at mental math. Okay. For this question,
Notation,
kind
brother.
of degree. Well, it doesn't have degree of freedom. Joe, good answers. Do you know the degrees of freedom? It's notation, brother, is the key, because you claim you can lose 10 pounds. That is the mu naught. Sample yields an average of this. This is y bar. That's the sample mean. Sample had a standard deviation of this, a standard deviation of the sample. 25 people, that is n. If n is 25, degrees of freedom are, everyone thinks that's OF, because I can't write, DF. Degrees of freedom is 24 because it equals n minus 1. And that's got it all, I think. It's everything noted right there. So the test for this is that the t statistic with n minus 1 degrees of freedom, which is just a subscript to tell us the shape of the t, is going to be equal to y bar, the difference of the sample mean minus the hypothesized mean, over the square s over square root of n, which is the standard error. So the sample mean was found to be 5.5. The hypothesized mean, oh man, 4.5. Oh no, it's negative 4.1. That's what I'm saying. Brian can't mental math. Brian got a number mixed up. Oh, and then I got the standard deviation wrong. Did I? I don't know. Let's just figure out what it is. It's close to negative 4. Because we are below, so it has to be negative, the observed results, and I'll highlight these real quick. Just note where everything goes. Understand you have to be able to read these problems here, because if you can't read the problem and understand the notation, that's where you run into problems. So the more problems you look at and you understand the notation and you can mark it all, and then you just plug it into a formula. So it's not that hard when you can mark the notation. If you can't mark the notation, these problems get super difficult very quickly. And just practice doing a problem like this or something. Write your own problems, have your friends do problems, see if you can get it and understand where the notation is. If you can do it, a lot better. So we're just going to solve this out right here. The top of the equation is 4.5, which is the difference. The test statistic is just a difference standardized, and we're going to divide by the standard error. This quantity right here is the standard error. Standard error of y bar. That's what s over square root of n finds. And so let's find it. See how close I was. So 6.1 divided by 5 is 1.22. I get close just by making mistakes. Kind of close. 4.5 divided by, and it has to be negative. So I got kind of close. Negative 3.69. Negative 3.69. So my guess, let's try to guess, it should have been a 6 here. And there we go. Just trying to do it quickly in my head, and I failed. I didn't get it. Now, this one right here, I beg of you. Please know our sayings. 1, 2. T, F. In a type 1 error, the null is true and we reject it. In a type 2 error, the null is false and we fail to reject it. To repeat those again, in a type 1 error, the null is true and we reject it. In a type 2 error, the null is false and we fail to reject it. So notice how there's 2 F's in the type 2. The type 2 errors when the null is false and we failed to reject it. 3 points. Memorize that. A small p-value provides stronger evidence against the null hypothesis. No text provided. I need to go update this question. Yeah, the lower the p-value, the more evidence against the null. It's against the null and for the alternative. Just the way it's worded, I'm a little bit worried. I know we write these questions, but sometimes when the p-value is low, you have evidence for the alternative. And that'd be evidence against the null. The way it's worded. What do we type into the chat for the formula sheet? Review 3 will send you there. Review 3 has it. So review 3, it has the formula sheet on the page. Be very careful. This one, the way it's worded, sorry, it's our question, I know, but I'm a little worried. A smaller p-value provides stronger evidence. It does for the alternative, but it is against the null. It's for the alternative. So you check the null. I'm gonna say true. I'm a little worried. And let's look at how that does on the analysis. If we construct a 95% confidence interval that does not contain the hypothesis value, which of the statements is true, we can reject it at the 0.05 level of significance on a two-tailed test. So we can reject it if it does not contain, and this goes back to the notes we were talking about earlier for the previous question, where on the two-tailed test, it's just 1 minus alpha. So if this was a 95% interval, you could use 0.05 on the outside, and that'd be analogous to a two-tailed test, which we usually do if we're not choosing sidedness, like a greater than or less than test. Only worried about one of them. We'll find out. Did I get it? Yeah, 10 out of 10. It's stronger evidence, and for the alternative, I would say. I'd preferably say stronger evidence for the alternative. Let's do another version right here. We did this one right here. We're trying to see it's less than, the null has equal sign. This one right here, notice it's square root of 25, and that means the standard deviation is going to be divided by 5. That's a standard deviation of 1.22. And, oh, is it the same? It's supposed to randomly generate. Give me the same exact thing? It randomly, no way. It did. Let's try it again. Give me the same question. It's supposed to randomly generate. We construct a 95% confidence interval, which statement it does not contain. That means we could reject it at the 0.05 level of significance because it doesn't contain the value. Type 2 errors when the null is false and we failed to reject it. The null is false and we failed to reject it. Low p-values are evidence of a cause and effect relationship. Type capital true or capital false. Low p-values are evidence of cause and effect. Capital will be like true or false. Low p-values are evidence of cause and effect. True or false in the chat for points. You get points either way. I got my hand on the point button. Low p-values are evidence of cause and effect relationships. 100% false. Good answers, Joe, right there. We'll throw you some extra points. Totally false. We don't like cause and effect in statistics. It's just evidence to reject the null because you can make errors, right? You could have a low p-value and make an error, so you don't know you should reject the null. We don't say cause and effect in stats. We don't like those words. Did I get? I did. I feel like that one was the same. It generated the same question. That's weird. Do one more preview right here. This one, they did generate different numbers. The difference, look at the difference between the null. I'm doing this one really quickly, check out where I did it slowly. I'm gonna try to do it in my head. Standard deviation is this, which goes to a standard error of 1.75. Bad words, you know those bad words. Oh man, oh, I can basically do it. So negative 0.96. Hopefully I'm close enough to it. Just get it. Less than evidence, that's evidence. Type 2 errors when the null is false and we reject it. And we fail to reject it. Oh my gosh, see, I can't even say it. That's false. Let's see if I got that one. You have to actually work. Do it? Nope. Oh, see, I was close. Did the math wrong. I'm doing it in my head, so I should have said, it's about -1. Let's see here. Let me try this one again. It's the same values. Why is it? It's supposed to have a ridiculous amount of values that it's choosing from. And I've got something's weird about this now to me because it's supposed to have a lot of values it chooses from. Like here you go. This is a different value. So that's a difference of 2.3. The top of the equation would be negative 2.3 divided by, and this would be 1.3. So 2.3 divided by 1.395 divided by 1.395. So that's 1 divided by 1.395 is 1 10/14, which is 5/7. So -1 and 5/7. 5/7 is 1/7 is 1/4, so 2.856. So it's probably about like that. Let's see if I got it. And I do them in my head. 14 years of doing math. Oh, off by a 10th. Off by a 10th. What was 10/14? Was I wrong about what 10/14 is? Yeah, I think that changed. Oof, I was pretty off on what 10/14 were. That's close. Yeah, we'll get one more try, Joe. Then I need to head out and we're doing interviews today. Big things happening around here. We'll do one more. So what I'm doing, if you're wondering how I'm solving this, I know I'm just having a little fun here to end, is I'm solving the top of the equation, which is the difference between the sample mean and the hypothesized mean. And then luckily with the sample size of 25, square root of 25 is always 5. So then I'm dividing that by 5, which you think 5 divided by 5 is 1. And then you get 1/5 when you divide the remainder. it'd be 1.22. The way sometimes people wonder, like, how do you do this? And it's just a lot of practice. You start breaking it down into parts. So what you can actually do is break it down this way. And so you just have to like track it in your head. And you say, well, how would you know what these things are? Well, 5 divided by 5 is 1. So this is the solve for it to do it in your head. You just break it into parts. And 5 divided by 5 is 1. So it's 1 plus, and then 1/5 is 0.2. So then it's plus 0.2. And then when you move the decimal in the 0.1, I think you just figured out this is 0.2, so that's 0.02. So that's 0.02. And so that's what I think through when I'm doing it. So when you hear me say 6.1 divided by 5. So I'm just doing a bunch of simpler math, but breaking it apart. I just basically go for the biggest thing I can get, which is the 5, and then I just go for the next decimals. Is that what long division is? I don't know. I never... So fun story one, I mean, we'll end with this, is I actually had a teacher early on think that I was cheating. They made a type 1 error because they came to me and they said, you didn't show your work. I think they even said, like, you can't use a calculator, you didn't show your work. And I said something like, well, I did in my head. And they're like, you did this in your head? And I was like, yeah, I just divided it out. And they're like, well, how'd you do it? And I go, here, I'll show you. And I wrote it like down. I was like, this is what I did. And they're like, that's what you did? And then I think they gave me another one. They were like, well, can you do this? And I was like, yeah. And I did that one. And they're like, oh, okay. I've always liked math. I think it's very interesting. And it's just a fun thing to like, it's fun to like test yourself to see like if you can get it. Like I like taking these quizzes sometimes just as like, can I guess it? That's the difference of 4.1. I'm just taking the difference right there. This right here is going to be 1.3. Thank you. 1.32. If you don't trust me, 1.32, or I'll check myself. 1.32. So it's negative 4.1. So right now what I'm holding in my head right now is negative 4.31 divided by 1.32. So what I'll do now is I'll start doubling it, and you can go in 3 times, and then the remainder after it goes in 3 times is going to be 0.037 is the remainder after it goes in 3 times. So we're already at negative 3. And then you can move this backwards for the next decimal to this right here. And then this can go, oh wait, no, that's not it's a 2. So now that can only go in twice. So the next decimal is this. And we could take a guess at the next one because it's going to be pretty large. We'll take a guess at 6, 3.26. It's tough holding all of it in your head sometimes. You have to be like repeating it and saying it out loud and like mumbling to yourself. So we should be kind of close to that. We wrote it down a little bit just to kind of show what we're doing. We'll either get, oh, what did I do? I did something wrong. Well, here we'll go look at the sheet. Well, I did something wrong. That should give the right answer unless I've really gone wrong, and then we're gonna have to head out. Oh no, I lost my HackerMan status. See, it's very easy to make mistakes. That's why you always want to check. Well, you see, that's what I said that was. Oh, did I get the difference wrong? Where did I get negative 4.31 from? Where did I get that? Okay, so I did that right. It's 4.4. No, it's 3.4. Wow. You know what I did wrong in my head? 10 minus 6.6. That's what I did wrong in my head. And I don't even know where I got the... I don't even know. My brain just... Yeah. So this is where we went wrong. That's where we went wrong. L HackerMan, 1,000 points right there. Well, we're going to end the office hours here. We'll do some more work next time. Big announcements to come. Stay tuned. Star Wars outro. 5 hours. We've almost got these new intros ready. We're almost there.
This has been going for like 20 hours. This ends now.